So direct evaluation, obviously your first move, and in rare instances, that'll be enough. So if I plug in 3 here, the square root of 3 plus 6 is the square root of 9 over 3 plus 2 is 5, and that'll just give you 3/5, and we're done. In the next exercise, -10, is there any problem? Oh, it's the same function, just -10. So you get the square root of -4 over -10 plus 2, which is -8. So this is imaginary, and we don't talk about imaginary numbers much with limits at all. So this just is, it does not exist. We don't know what this function looks like verbatim, but what could we say, generally speaking, is the reason that that limit doesn't exist from a visual perspective? Does it not exist because it's an asymptote? No. Why doesn't it exist? Not really so much the roots, Josh, but we're getting warmer. Josh? Right. The function doesn't exist at -10. It's not about the root so much as that the function doesn't even exist. The function doesn't start existing until -6 and bigger. So anything under -6, your limit's not going to exist because the function doesn't exist there. So now knowing that, obviously what's going to happen at -6? Will the limit exist? No. It won't, because we know that that's where the graph begins. So the limit from the right will exist, but the limit from the left will not. However, I will warn you that if you plug in -6 and do direct evaluation, you would get an answer, but it would be misleading. So direct evaluation is obviously great, but you have to be also always weighing in what you know about the visual of the graph. Does this make sense? If I were ever to plug in -6, I would get 0 over -4, which would be a limit of 0, you would think. But you always have to have in the back of your mind, weighing in on you, what you know about limited domains and the images and where the function might not exist, where the function might have an asymptote, all of those things. Okay? The only other point of interest I can think of is -2, because that's going to be an asymptote. If you plug in -2, you're going to get 2 over 0, which is undefined, which is a limit does not exist type scenario, but then we need to get more specific about positive or negative infinity, right, as you approach -2. Okay? Is it going to be the same behavior on either side of -2 or different? And how do you know? On either side of the asymptote at -2, will it have the same behavior or different, and how do you know? Jalen? Let's do, yep, it's a single power. It's x plus 2 to the degree of 1. So that means that the behavior on either side will be different. If you wanted to plug in points to check it, you could plug in -1, which would give you a positive over a positive. So coming from the right, it would be going towards positive infinity. To the left of -2, if you plugged in -3, you're going to get a positive over a negative, which would mean negative infinity. Okay? So just for the sake of getting a full idea of what this looks like, I'm going to show it to you on the graph. I'm going to give you a window of -10 to 10. And, oh boy, let's do -10 to 10 as well. We'll just do a standard window and adjust it if we need. Okay, so we obviously have our asymptote, and we have, it looks like it's kind of going towards negative infinity, but it actually stops right here. So if I were to zoom in a little bit more and go maybe on my y-axis from -3 to 3, I think you'd see a little more clearly how it just flat out stops when it hits that 0. Okay? What about horizontal asymptotes, since we know about those? What is the degree rule on this function? Is it small over big, big over small, or same over same? Small over big. So we should have an asymptote at 0. And we do, and it guides the end behavior going towards infinity, but not the end behavior going towards negative infinity, because that piece about the function not existing over there has to weigh in. Okay? If you kind of looked at the limit as you went towards infinity, what do you know it is just by looking at the graph? The limit as x approaches infinity is as you go towards infinity, behavior is guided by that asymptote, so it should be 0, right? Knowing what we know about the horizontal asymptote rule, this is, I mean, maybe you think it's, but we're only going to 10. If I went from negative 100 to 100, you'd see that this kind of becomes one and the same with the x-axis eventually. Okay, so it's not at 1, it's at, and actually, let me back up, negative 10 to 10. I only went from 1, 2, and 3, so 1 is here anyway. For those of you that answered 1, remember what my scale was? This is 1, 2, 3, so we've already gotten below 1. The idea of plugging in an infinite number should make sense here as well, because if we plug in, or does it? If you think about plugging in a humongous number, like 1,000,000, you've got the square root of 1,000,006 over 1,000,002. So, which one's growing at a faster pace? The bottom one, right? This one's still growing pretty significantly, but not as at as fast of a pace, because the square root is kind of cutting down on that. So if they're both growing, but your denominator is growing that much faster, then the gap between them keeps growing and growing and growing, and then it approaches 0. When the gap between your numerator and denominator keeps growing, with the denominator being the larger one, you're approaching 0. So that argument works if you plug in a number towards infinity, but it's maybe not as confident as we'd like it to be. But again, it should still always weigh in and help inform your decision. All right, so I just want to look more into that, because here's the first trig that we've really come across, but this is with direct evaluation, so we can just plug in 7. And the secant of 7 pi over 6. Got to go back to our trig mode. 7 pi over 6 is in what quadrant? 3. With a reference angle of pi over 6. Secant is the reciprocal function to what? Cosine. So should this be positive or negative? Negative. And what is the cosine of pi over 6? Radical 3 over 2, and so we need to reciprocate that for the secant. So rather than radical 3 over 2, we do 2 over radical 3, and then we have to rationalize. So negative 2 root 3 over 3 is our limit. And then direct evaluation on a log function. Log of 1 over e to the first. Think back to natural logs. What do they have a base of? E. And this is the same as e to the negative first power, right? So it's the natural log of e to the negative first power. So your natural log and your e just cancel, and your answer is negative 1. So it's been a while, but obviously log rules and all that good stuff, trig calculations are still on the table. Okay? And below this we have compositions, which came up in the PreCalc book, but not a ton of it. It kind of makes sense. If I just jump right to C, and I want the limit as x approaches 4 of g of f of x, that's taking the f of x function and plugging it into g. So if I take the f of x function and plug it into g, that's going to be the function cubed root of 2x squared minus 3x plus 1 plus the 6. And then you really just directly evaluate. Combine like terms, simplify that new function, that new composition function out, and just directly evaluate. So the cubed root of 2 times 4 squared is 2 times 16, which is 32. Minus 3 times 4 is minus 12, plus 7. What did I do wrong? Yes, I did. Notationally. Liam. Right. I shouldn't have written this limit as x approaches 4 because I'm in the process of directly evaluating. So I should have lost that there. So 32 minus 12 is 20. 20 plus 7 is 27. So it's the cubed root of 27, which is 3. So they like to illustrate splitting it up into 2 functions. So just illustrating that you can take the limit working inside out, take the limit of the f of x function first, which would just be plugging in your 4. So 2 times 16 is 32, minus 12 plus 1 puts you at 21. And then, like as you would for a composition, now you find the limit of g of x as x is approaching 21. And you get the same answer doing it as a 2-step process. But I honestly think that that's more trouble than it's worth. They're just illustrating that the composition of function concept of doing it as a 2-step process still works under limits as well. I would just jump right to it though. I would just rewrite the new function and then plug into that. It'll end up the same. All right. Our limit properties, which we learned, they haven't come up a ton since, but they'll continue to come up sparingly. They can be found on page 76 of your textbook, but then I went ahead and decided to write them down at the bottom anyway. So they're presented a little bit differently in this calculus book, but they are all the same properties. This tells us that the limit of f of x as we approach c is going to be defined by capital L. And the limit of g of x as we approach c is going to be defined as capital K. So if you're looking for the limit of your function f, but there's a coefficient of b out in front, then you can just take the limit of your function, which is L, and put that coefficient b in front of that limit answer, and that's the same thing. The addition subtraction, you can kind of split it up, so you can take the limit of f of x separately and the limit of g of x separately, get your L and K, and then add those together if it's a plus, or subtract those if it's a minus sign. This book also condensed those plus and minus properties into one, which the PreCalc book kept them separate. With multiplication, the limit obviously can be found separately, and then you just multiply your 2 individual limits together. Division, same thing. The only stipulation with division is that g of x's limit can't equal 0. So that k value cannot equal 0 for the obvious reason of you can't divide by 0. And then if your function is being raised to a power, you can find your limit of the function first and just raise that limit to the power, and it will be the same thing. You know what just dawned on me? Just a connection I just made that I'll show you. This could be perceived, rather than just thinking of it as the coefficient being brought out in front, this could be perceived as multiplication, right? B times f of x. So according to our multiplication rule, that would be the same thing as the limit as x approaches c of b times the limit as x approaches c of f of x. Now this is L, and we learned back in the pre-calc book that the limit of any constant is what? Just that constant. So you kind of get that BL from that multiplication rule as well. Yes? So, what do they get? There's questions like this on your homework. Find the following, recalling the limit properties. So, they're telling us that the limit of f of x is 27. So, using our limits rules, we can take the limit of f of x first, and the cubed root is just like an exponent, right? So this would be using property 5. We'll just take the limit of the function first, and once we have that limit, we'll raise it to the 1/3 power. And again, they just told us that this was 27, so that's just 27 to the 1/3 power, which is 3. In B, it's the division property. Well, you could kind of look at this both ways. You could look at this also as a coefficient of 1/18. So if you wanted to use the first property down there, you could look at it this way and let it just be 1/18 times your f of x limit, which is 27. That would be 3/2. Using property 4, the division one, you take your limit of f of x and divide it by your limit of constant 18. So this is 27. Limit of any constant is the constant, and you still get 3/2. C is definitely the last property. Just take your limit as x approaches c of f of x, and whatever that is, just square it. So that's 27 squared. Uh-oh, I don't like that. You guys are on the ball. I would probably say, if this was without a calculator, another way I could write it as 3 to the 6th power. Might also be a multiple choice option, right? You get 27 squared, and let's pretend that the numbers are even bigger and you couldn't do 27 times 27 out. They might not have 729 as an option. They might have 3 to the 6th. Does everybody see that? Okay? So just knowing how they may present things. And then this last one, your limit of f of x is 27 to the 2/3 power, and that we should be able to take the cubed root of 27 first, which is 3. 3 squared is 9. Okie doke. 15 minutes. I'm tempted. Don't do it with this right now. Don't do it. I'm going to do it. This will give us another day to review. No, apologize. What is going on here? No. What? By the way, sisters and brothers, don't. Okay. So all of that was review. So that was very boring. Liam, I lost you there. Did you get a good snooze? All right, good. Don't let me lose you here. So this particular problem, direct evaluation, let's see what happens. E to the 0 power minus 1 over e to the 0 power minus 1. 1 minus 1 is 0 over 0. Surprise. So one of the first methods of manipulating, once we got the indeterminate case, was factoring. And this doesn't look like the traditional factoring problem, but this can be factored. How? The numerator is the, yes, Liam? Right. The numerator is the difference of perfect squares. Get over that. You see it now? E to the 2x has a square root of e to the x, and 1 has a square root of 1. So it's two perfect squares and the difference between them. And when you factor into those conjugates, now we have this beautiful thing happening. And now we can re-plug in the 0. E to the 0 plus 1. 1 plus 1 is 2. So the limit as x approaches 0 of this function is 2. Let me show you. E to the 2x power minus 1 divided by e to the x minus 1. Zoom 6. Look at that. Good? Because this function simplifies to just this function, which is a parent graph we know, right? An exponential function with some base to the x power shifted up 1. We just have a whole. Where's our whole? What's that? Well, the whole was caused by that, but you find out the whole by plugging 0 into the new function, right? This function, just this, and the original are going to look exactly the same with the exception of at the whole. Well, the whole is at 0, right? That's why we got indeterminate at first. You plug in 0 to that simplified function. E to the 0 is 1. 1 plus 1 is 2. Your whole is at 0, too, which is why your limit can exist, even though the function value does not. Okay? Anytime you directly evaluate and you get the indeterminate case, that means that the function value doesn't exist there. But sometimes the limit still can. Okay? I was highlighting, I talked about this on when we just went over your homework, but this is just a different presentation where they kind of save that vertical space. So I think it's easier for you guys to see if you do kind of change it so that you can see the complex fractions a little bit more clearly. Now plugging in 0 is going to give us the indeterminate case. So manipulation in this context is just by clearing those complex fractions. What do I multiply by, Ellie, to clear the complex fractions? Four to the what? Yeah, you're not clearing. You're trying to get a common denominator, then do the subtraction, and then you're going to keep change flip. But if you're clearing fractions, we're looking for of the denominators within the fraction, which we have 2. What is the least common denominator of those two denominators? And that would be a 4 and an x plus 4. So we multiply the overall numerator by that, which is going to require distribution, and we multiply the denominator by that, which we will not distribute out because we're not clearing any fractions there. So when we do that up top and distribute this to the first term, the x plus 4's cancel and we just have 4. When I distribute to the second term, my 4's cancel and I just have minus, most importantly, a binomial that needs to be kept in parentheses so that we don't forget to distribute that minus sign because those 4's just cancel. And then on our denominator, we're going to keep it x, and I'll put the 4 out in front of that x, and then x plus 4. I'm not going to distribute this out. Continue simplifying in the manipulation, and your 4 minus your 4 cancel. So we just have the limit as x approaches 0 of negative x over 4x, x plus 4. And our problem, which was that factor of x, cancels. And so now plugging in 0 should not be an issue. You now plug in 0 to reevaluate, and we get negative 1 over 16. Okay? So a review there of clearing fractions. What do you make of this example? What's different about that to you? That's correct. And in math, does anybody know what that triangle symbol means? Change, exactly. So what I know and what you can kind of make sense of now, because we have already done derivatives, we're used to doing the limit for derivatives as h approaches 0, h being the change in the x coordinate, yes? Remember that with the derivatives, how h was defined as the distance between our two x coordinates. So here's x, and this is x plus some h value. And that h distance between those two x coordinates was pinching in towards 0. This is just a notation that does come up just so you're not thrown off by it. That change in x is just like your h. It's really just like any variable. The same thing needs to happen. You try to directly evaluate. If the change of x is approaching 0, you plug in a 0. Now, direct evaluation, per usual, it's going to get you 0 over 0. But we can potentially try to manipulate. How would you manipulate this? Thoughts, Taylor? Let's try it. Anybody have another thought? Liam? Yeah, maybe just multiplied out. That could have caused something, but this might as well. But this is going to create x plus change of x to the 6th power minus x to the 6th. Did that help you, Taylor? Not a bad thought, because we've been doing stuff with conjugates. Conjugates is more for rationalizing, I'll be honest with you. And there's no radicals to rationalize here. So I like Liam's idea. I think it will work. Does anybody see another option? Maybe. Because that was not my first instinct. Although I think it will work, Liam. I just don't feel like cubing something. How about factoring? Difference of perfect cubes. Do you see it now? Again, not sure it'll work, but I think it probably will. My gut says it's going to. So if I factor this, what's the cubed root of this? X plus change x, right? Minus, what's the cubed root of this? X. Then my trinomial consists of this squared plus the product of this and x plus x squared all over change in x. So what happens here is, in our first term, x minus x cancels, leaving just a factor of the change in x. Do you follow? And that will now cancel with our denominator. So now we can directly evaluate just by plugging in 0 for change of x. So that will be x plus 0 squared plus x times x plus 0 plus x squared, which is going to be x squared plus x squared plus x squared, 3x squared. Oh yeah. We'll do a lot of shortcuts. A lot of rules to remember coming down the pipe. Okay? On page 85, I like these types of problems. And we do this with your work all the time. But take a look at number 68 and see if you can find the mistake. Jalen. Right here. Yep, they just factored wrong. So if you're looking quickly, like I remember the first time I looked at this, I'm like, okay, they factored, they canceled, they plugged in, they got this answer, and I was like, wait, what's wrong with that? How many people thought that? How many people overlooked how they factored at first? And I was looking at the general scope of the whole approach, and their understanding of how to find a limit is correct. What they screwed up, obviously, was just the Algebra 2 topic, really, of factoring. All right, here's how we're going to fix your homework. This is what the bottom of the 2 pages say. They say odds. We're going to cut down odds to 5s, 9s, and 3s. We're doing both, but we're cutting down to 5s, 9s, and 3s. And some of these direct evaluation ones that don't require any manipulation will be super fast anyway. So I don't think it'll be crazy. Okay?